Objective 12.4, Introduction to Probability. In today's objective, we want to be able to find the theoretical and experimental probabilities of a situation. We also want to be able to find geometric probabilities. So a little bit of definition first. A probability of an event is a number between 0 and 1 that indicates the likelihood that the event will happen. If I have a probability equal to 1, then we can say the event is certain to occur. If I have a probability equal to 0, then I know it is impossible for the event to occur. And if I have a probability of 1/2, that tells me the event is equally likely to occur or not occur. So obviously numbers below 1/2 are less likely to occur, and numbers above 1/2 would be more likely to occur. Theoretical probability happens when all outcomes are equally likely. The theoretical probability can be found using this equation. Probability of event A equals the number of ways we can get A as an outcome over the total number of outcomes in the situation. So graphically we can look at it like this. This large oval represents all of the possible outcomes. This shaded oval represents event A, and each dot represents an actual outcome. So if I want to know the probability of A, the number of outcomes in A is 4. 1, 2, 3, 4. The number of total outcomes is not only the 5 out here, but also the 4 here, because that's all inside of my large oval. And so I would say the probability of A happening is 4 over 9, over everything. Now usually we call theoretical probability just probability of an event. If it's something different, if it's a specific type other than theoretical, that's when we specify the type. So anytime you just hear someone asking for probability, we can assume they're talking about theoretical probability. So let's take a look at an example. It says you roll a 6-sided die whose sides are numbered 1 through 6. Find the probability of rolling a 4, an odd number, or something less than 7. So following our formula that we just saw, if I want to know the probability of rolling a 4, I would say how many ways can I get a 4 when I roll a die over how many different possible outcomes there are when I roll a die. Well, since there's only one 4 on a die, we would put the 1 on top. Since there are 6 total possible numbers on the die, we would put the 6 on the bottom, and our probability then would be 1/6. If I apply the same logic to the probability for an odd number, the number of ways I can get an odd result are 3. I could have a 1, I could have a 3, or I could have a 5. So there's 3 different outcomes that would be an odd number, still over 6 total possible outcomes. So 3 over 6 can be reduced to 1/2. So this is a case where I am equally likely to get an odd number as I am to not get an odd number, to get something even. In part C, the probability of rolling something less than 7, well, all of the numbers on the die are less than 7. So I have 6 ways of having this event occur over 6 possible different ways. This reduces to a probability of 1, and that makes this a certain event. Every time I roll the die, I am certain to get something less than 7. When we are writing probabilities, we are allowed to express probability either as a fraction, as we saw here, as a decimal, or as a decimal turned into a percent. Which form you use really just depends on how you're finding the numbers, what numbers you're using to find it, and what kind of answer fits best for the problem. Let's take a look at another example. Here we're going to combine finding probabilities with permutations and combinations. So here's our situation. 4 cards are drawn from a standard 52 card deck. We want to know what is the probability that you draw a jack, queen, king, and ace of the same suit in that order. So again, if we think about how to set up our probability, we need to know how many different ways can I get a jack, queen, king, ace of the same suit in order, and then put that over the total number of ways that I can draw 4 cards in order. So total ways of drawing 4 cards also in order. Okay. Well, let's think about our jack, queen, king, ace here. How many different ways can I draw a jack, queen, king, ace, same suit in order? Well, you're looking at it right here. There's only 4 ways that can happen. If I have to be in order, then it only is going to happen once for each suit. So my top number is just going to be 4. But for my bottom number, the total number of ways to draw 4 cards in order, to find that, I can use a permutation. So I'm going to set up the permutation of 52 cards taken 4 at a time. And then I can work out to get that number, which is 6,497,400, and then take the 4 divided by that, and we end up with a decimal of 0.000000616. So with such an incredibly small probability, the likelihood of this happening is practically impossible. All right, let's take a look at another example. We're still drawing 4 cards, but this time we want to know what is the probability of drawing 4 cards of the same suit regardless of order. So there's a couple of things here. First of all, when we see phrasing like regardless of order, that's a pretty good clue that we're talking about a combination rather than a permutation, because order is not going to make a difference. We also have to realize here that it can be any 4 cards within a particular suit, and it can be any of the 4 suits. So when we go to set this up, we have to take both of those things into consideration. The fact that there are 4 suits to choose from, and we want to choose one of them, and the fact that within a single suit there are 13 cards to choose from, and we want to choose 4. So when we set this up, we're looking for the number of ways to get 4 cards in the same suit, still over the total number of ways of drawing 4 cards. Okay, but now it's 4 cards in any order. So notice our denominator has changed from being a P to being a C. 52C4. 52 cards taken 4 at a time in any order. Also notice our numerator now. Our numerator is the product of 2 different combinations. The first combination tells us how many different ways we can choose a suit. The hearts, the diamonds, the clubs, the spades. So there are 4 suits to choose from. We're taking one of those. So that's going to be one combination. And then once we've made that choice, then we have to think how many ways can we choose 4 cards out of the 13 cards in that suit. So we need to multiply those 2 numbers together to get the number of total ways we can get 4 cards in the same suit. So when we work that out, we take the 13C4 and then multiply that by the 4C1. Well, this is just 4. There's 4 different ways to choose a suit because there's 4 different suits. Take that 4 times the result from 13C4 and we get 2,860. And then that's going to go over 270,725 because we're now talking about combination, not the permutation that we had Whoops, sorry. Went too far. Right? Not the permutation that we had here where we had 6 million different ways because order made a difference here. Order doesn't make a difference anymore. We can get 4 cards in any order. So as a combination, our denominator is going to be 270,725. And when we divide this out, we end up with a decimal of about 0.01, which is about 10%. So you have about a 10% chance of this happening. Much better chance than our previous example. All right, final example. This has to do with geometric probability. This happens when we are trying to find probability based on geometric shapes or situations. So here's a case where we have a dartboard. It's a square board. It has rings on the inside, each worth different amounts of points. And I apologize, I did not label the points on your page in your guided notes, so you may want to label that as 10, and then the next ring is 5, and then 2, and then if you're outside of the rings, you get 0 points. Okay? You can also see here, even though it may not look exactly to be the case, we're assuming that each ring is 3 units wide. Okay, so the question here is, are you more likely to get 10 points in the bullseye or 0 points out here on the corners? So let's figure out what the probability for 10 points would be. Since my dart is equally likely to hit any point inside the square board, any point in here would be referring to area. So in order to find the probability of getting 10 points, I need to figure out what is the area of the bullseye, which is the smallest circle, and compare that to the area of the entire board. And so for the smallest circle, we can see we have a radius of 3. So the area of that circle is going to be pi r squared with r equal to 3. Then the area of the entire board, since this is a square board, we know it's going to be side times side. But how long is one side? Well, we can use our measurements here to figure that out. We know that this has to be the center if we're labeling these widths. So we know from the center out to a side, we're 9 units across. So that must mean from the center out to this side, we would also be 9 units, and therefore from side to side, we would be a total of 18 units across. So if one side is 18 and this is a square board, that means the other side would also be 18, and I can find the area by taking 18 squared. So now I work this out. I'm going to get 9 pi on top, 324 on the bottom, and when I divide that out, that gives me a probability of about 0.0873. Okay, now let's figure out the area, or excuse me, the probability of getting 0 points. 0 points happens if I hit one of these corners. So in order to find the area of those corners, I'm really taking the area that is outside of the largest circle. So not a particular circle in and of itself, but the area outside of this largest circle. And again, comparing that to the area of the whole board. So in order to find the area of those corners, I need to set it up this time so that I take the area of the board minus the area of the large circle. That's going to represent the area that is left for these corners. So again, the area of the board would be 18 squared. And now my large circle has a radius of 9. So I'm going to subtract from that pi times 9 squared, which is 81 pi. And the area of the entire board is still 18 squared on the bottom. And so when I work this out, I get approximately 0.215. So when I compare that to my probability for getting 10 points, it becomes pretty clear that I am more likely to end up with 0 points than 10 points based on the areas of those regions. So that's an example of geometric probability, where you're using geometric means like finding area in order to figure out the probability of your event occurring.